Hello everyone, welcome back to SHR Trinity. In today's video, we are continuing our machine learning interview questions series. This is part 5, the final part of our series, where we will cover expert level and real-world scenarios, specifically questions 41 to 50. We will dive into machine learning pipelines, production deployment patterns, concept drift, data leakage, class imbalance strategies, explainable AI, MLOps, and how to design end-to-end ML solutions. Let's study these expert topics in detail. Before we dive into the questions, let's look at what we'll be covering in this video. We will discuss expert level and real-world scenarios. We will cover machine learning pipelines, deployment models, concept drift, data leakage, class imbalance handling, explainable AI, feature importance, MLOps workflows, the end-to-end project lifecycle, and how to design a complete machine learning solution for a business problem. Question 41. What is a machine learning pipeline? A machine learning pipeline is a software design pattern used to codify, organize, and automate the sequence of operations required to transform raw data into predictions. In a typical project, you must impute missing values, scale numeric columns, and one-hot encode categorical features before feeding the data into a model. A pipeline bundles all of these individual pre-processing transformations, along with the final machine learning estimator, into a single, cohesive workflow object. This encapsulation is vital because it guarantees that the exact parameters learned from the training split, such as the median values used for imputation or the means and standard deviations used for feature scaling, are applied identically to the test and production datasets. This completely eliminates the risk of data leakage and ensures that the model behaves consistently across development and production environments. In Python, pipelines are commonly constructed using scikit-learn's pipeline class combined with a column transformer to apply different steps to different feature types. Question 42. How is a machine learning model deployed? Model deployment is the process of integrating a trained and serialized machine learning model into a production environment so that it can receive input data and return predictions. There are 3 primary deployment patterns. First, real-time inference, where the model is serialized using libraries like joblib or ONNX, and hosted behind a web service using frameworks like FastAPI or Flask, running inside Docker containers. Clients make HTTP requests with featured data and receive predictions instantly with millisecond latency. Second, batch inference, where the model runs offline periodically, such as hourly, daily, or weekly, to process massive amounts of data in a database, saving predictions for later retrieval. This is highly efficient when instant decisions are not required. Third, edge or embedded deployment, where the model is compressed and runs locally on consumer devices, like mobile phones or smart sensors, using lightweight runtimes like TensorFlow Lite or ONNX runtime. This pattern is ideal when internet connectivity is unreliable or when data privacy is paramount, as no data needs to leave the device. Question 43. What is concept drift? Concept drift refers to the phenomenon where the statistical properties of the target variable change over time in an unforeseen manner, causing the model's predictive accuracy to degrade. Mathematically, it means the conditional probability of the target given the features, p of y given x, changes. It is crucial to distinguish concept drift from data drift, which is also known as covariate shift. In data drift, the distribution of the input features, p of x, changes over time, but the underlying relationships remain the same. In concept drift, the inputs might look identical, but the actual relationship between the inputs and the target variable has evolved. A classic example is a consumer purchasing model trained before the COVID-19 pandemic. During the pandemic, buying behavior changed drastically due to external factors, rendering the pre-pandemic models highly inaccurate. To detect concept drift, we must continuously monitor model accuracy in production, calculate statistical distance metrics like the Population Stability Index, and establish automated pipelines to retrain models using the latest training data. Question 44. What is data leakage? Data leakage, or target leakage, is one of the most common and damaging issues in machine learning. It occurs when information from outside the training dataset is used to train the model. This typically results in an extremely high, almost perfect validation accuracy score during development, but exceptionally poor accuracy once the model is deployed to production. A classic cause of data leakage is applying preprocessing steps, such as computing the mean and variance for feature scaling or calculating target averages for categorical encoding, on the entire dataset before performing the train test split. When you do this, information from the test set leaks into the training calculations. In time series forecasting, data leakage occurs when future information is accidentally used to predict past events, such as including tomorrow's price as a feature to predict today's trend. To prevent data leakage, developers must split their dataset into train, validation, and test sets first, and ensure that all scaling and imputation parameters are computed solely from the training partition. Question 45. How do you handle class imbalance? Look at the comparison table on screen. Class imbalance is a frequent challenge in real-world applications like credit card fraud detection or medical diagnosis, where the positive class represents a tiny fraction, often less than 1%, of the total dataset. If we use standard accuracy to evaluate the model, a dummy model that predicts legitimate or healthy for every row will achieve 99% accuracy, despite failing completely at its task. To handle class imbalance, we can use three approaches. At the data level, we can use resampling techniques, such as undersampling the majority class to balance the ratio, or oversampling the minority class using synthetic generation methods like SMOT, which stands for Synthetic Minority Oversampling Technique. SMOT creates synthetic samples along the lines joining existing minority points. At the model level, we can adjust class weights in the loss function to heavily penalize errors made on the minority class, forcing the optimizer to focus on them. Finally, at the evaluation level, we must abandon simple accuracy and instead optimize for precision, recall, F1, score, and area under the precision recall curve. Question 46. What is explainable AI? Explainable AI, or XAI, refers to a set of methods and techniques that make the decisions made by machine learning models understandable to human experts. As we deploy highly complex models like deep neural networks, random forests, and XGBoost, they act as black boxes, making highly accurate predictions but giving no explanation as to why. This lack of transparency is unacceptable in high-stakes industries like healthcare, finance, and criminal justice, where decisions must be audited for bias and compliance. XAI addresses this using two main techniques. Local interpretation explains why a specific individual prediction was made, using frameworks like LIME, which fits a simple interpretable model locally around the prediction. Global interpretation explains the overall behavior and feature relationships of the model, using frameworks like SHAP. SHAP is based on cooperative game theory and Shapley values, calculating the exact mathematical contribution of each feature to the final output, ensuring that complex model decisions can be fully trusted and audited. Question 47. What is feature importance? Feature importance is a metric that assigns a score to each input feature, ranking how valuable it was to the model's predictive performance. In tree-based models, feature importance is commonly calculated using mean decrease impurity, which measures how much a feature's splits reduce impurity across all trees in the forest. However, this method can be biased toward high cardinality numerical variables. To address this, we use permutation feature importance. This method shuffles the values of a single feature in the validation set, breaking its relationship with the target, and measures the resulting drop in model accuracy. If shuffling a feature causes a massive drop in accuracy, that feature is highly important. Permutation importance provides clear, model-agnostic insights, allowing developers to simplify models by removing redundant features, explain predictions to stakeholders, and focus feature engineering efforts on the most impactful variables. Question 48. What is MLOps? MLOps, which stands for Machine Learning Operations, is a set of practices that aims to deploy, run, and maintain machine learning models in production reliably and efficiently. It represents the intersection of machine learning, software engineering, and DevOps. MLOps bridges the gap between model development and software operations. It automates key phases of the project, establishing continuous integration and continuous deployment pipelines. When a data scientist updates model code, the pipeline automatically packages the model, runs unit tests, evaluates performance, and deploys it to staging or production. Additionally, MLOps implements continuous training, monitoring incoming data in production for data drift or concept drift, and automatically triggering a retraining pipeline when metrics drop below a set threshold. This ensures models remain accurate and robust in changing real-world conditions. Question 49. Explain the end-to-end machine learning project lifecycle. A machine learning project is not a one-off scripting task, it is a continuous, highly iterative lifecycle. The lifecycle begins with Phase 1, defining the business problem and selecting the correct target evaluation metrics. Phase 2 involves data ingestion, exploratory data analysis, cleaning, resolving missing values, and labeling. Phase 3 is the core modeling phase, where we perform feature engineering, train multiple candidate models, and tune hyperparameters. Phase 4 is validation, where the model is evaluated on a holdout dataset, subjected to compliance reviews, and prepared for stakeholder approval. Phase 5. Question 50. How would you design a complete machine learning solution for a real-world business problem? When designing a production-grade machine learning system, the training code is only a small fraction of the overall system. A complete solution must be designed systematically. First, the data ingestion layer must handle raw data collection, using batch orchestrators like Apache Airflow for scheduled processing, or streaming platforms like Apache Kafka for real-time data ingestion. Second, the serving layer must match business latency constraints. We choose real-time REST APIs using Fast API for instant predictions, or offline batch processing for massive volumes. Third, we must build a monitoring layer that logs model inputs and outputs, calculates drift metrics, and sends alerts to developers. Fourth, we must implement a robust fallback mechanism. If the machine learning service experiences high latency or crashes, the system must immediately redirect requests to a simple, rule-based heuristic model to maintain service availability and ensure business continuity. Thank you for watching. If you found this video useful, please subscribe to SHR Trinity for more videos, and click the like and share buttons. Congratulations on completing the machine learning interview. If you are interested in attending our live training sessions or have any inquiries, all our contact details are displayed right here on screen and are also available in the video description below. Feel free to reach out to us. We would love to have you as part of the SHR Trinity learning community.